In this video we're going to look at surface integrals. So imagine we had a ball just sitting in space. So there's a z, x and our y coordinates. And we were to approximate this ball just using a lot of squares. So all of these squares will just sit tangential to the surface of the ball, and you could imagine that as we increased the number of these squares to infinity and made the actual area smaller, then this would approximate this smooth ball. So if the ball also is sitting in some vector space, so every point in this space here has associated with it a vector. So there's a vector there, they're all in pink. And I've also drawn in one of the surfaces here, and we've drawn in the normal to the surface. So at this junction here, at this point where the normal is, well, that will also have a vector associated with it from within this vector space. So I've drawn both of these out here. So we've got our little area here, so we can call our area delta S and L for a subscript for the Lth area element. And we've drawn in a normal here, and we've drawn in the vector for this function f xl, yl and zl. Now we know from what we've done previously when we looked at Gauss's law, what we're going to do is we're going to take the vector function and we're going to find the normal component of the vector function. So it's going to be f dot n. So f is a vector function and it's dependent on x, y and z, and n is the normal, and again it's dependent on the position x, y and z. So we've drawn that up here, and you can see that if you were to take the normal component of the vector here, it's like taking the value of the function f but in the direction of the normal. So we can drop the perpendicular down here, and we're looking at f dot n would be this length here. Okay, so that's the component of the vector f in the direction of the normal n. Now if you're unsure about the dot product, there's a video which if you click on just up here, we'll take you through the snippet section and you'll be able to go in and see a derivation of the dot product. Now let's imagine we take this f dot n and we multiply it by the area element delta s, and then we sum up all of those area elements from L equals 1 to some value n. And then finally what we can do is we can take the limit as the number of the elements, the area elements, tends to infinity, and the actual area of each element tends towards 0 over function. So whenever we do that, we're going to be left with is we take the limit process, we're going to end up with the surface integral of the normal component of the vector function by ds, which is our surface integral. Now, one thing to note as well is that by convention, you can note that the normal component on a closed surface could point out the way, or it could point in the way, and again by convention we decide that the normal component will point outwards from the surface that encloses a particular volume. So let's look at a simpler surface integral. Rather than looking at a vector function, we're going to look at a scalar function here of x, y and z. So let's consider that we have mass per unit area was given by sigma x, y and z. So the mass per unit area is dependent on the position. Then we could find the total mass by multiplying the mass per unit area times the small unit area delta SL and summing those from L equals 1 to n. And again, if we were to take the limit as the number of elements, the area elements, tends to infinity, and the actual area of each element tends towards 0 over delta over sigma delta s, then we're going to get the surface integral of sigma xyz by ds, which would give us the mass of a surface. Now let's move on. Now we're going to look at a neat way of evaluating surface integrals. So let's say, for instance, we've got our x, y and z plane, and we've got some simple function, so z is a function of x and y, which gives a surface here. Now let's consider we take a small part of that surface, we just call that part of the surface delta s. Then we can project that surface down onto the xy plane, and it'll give us another surface here, delta r, which of course is not really a surface, it's just going to be an area element within this plane xy. Now we're going to ask the question, how can we relate this surface area here to this surface area delta s to this area delta r? Now the way you can kind of think about this is that if you look down from above, then, and say shine a light down on the surface, then what we're going to be looking at here is the shadow of this surface. Now you can see that these two are going to be different. So let's take an example of, say, a map. If you have a map of the UK, and if you look at that map of the UK, then you can work out the area of the UK from that map. But that area there would be this area delta r. That area would be different from the actual surface area, because whenever you come down onto the surface of the planet and you are walking about in the UK, you'll notice that it's hilly, and the mountains will create an extra area, when that area would be our delta s. So let's look at how we can work out the area, the relationship between our delta s and our delta r. So what we're looking for is a relationship between s and r, so that we can relate the surface integral to just an ordinary double integral over some region r. So again, let's take our x, y and our z coordinates, and let's draw out a surface here. So you can see these yellow lines here. I've just drawn out one particular surface, and we say that that area of that surface is going to be the length there, a, divided by that length, the breadth there, b. So the area delta SL is just going to be a times b. But if we were to look down, and that's meant to be like a little eye looking down, so if we were to look straight down, then what we would see would be this area here. So this would be the projected area onto the xy plane. So that area then would be a, which remains the same, but it'd be length b dash. So that's this length here. And you can see this length b dash is shorter than our length b. So what we want to do is we want to relate the area AB, which is this area up here, to the AB dash, which is relating the area delta SL to delta RL. Now we can use a bit of simple trigonometry, because we can see that the B dash, which is this length, divided by B is just the cos of this angle, theta. And that angle there is just the angle that the plane makes with the x-axis. So then we can rewrite that as b equals b dash upon cos theta. And then if we multiply both ends by the a, then we've got a relationship between these two areas. So it's going to be AB is going to be AB dash upon cos theta. Now here's another neat little trick which I think is quite nice. If we were to draw the normal component to this surface here, and then we were to draw the component in the z direction, which is the k component, then this angle here would be the same as this angle here. And we can get that angle by taking the dot product n dot k. Now you can convince yourself of that, because if you were to think this angle here is tending towards 0, so this surface here just tends to get flatter and flatter, then you could see that when it's completely flat, as in it's sitting in the xy plane, that means that this normal component will sit along the same axis as this k component. And then if you were to start moving it up, you'll see that the normal component will start moving along with this angle. So you can see that this angle here will be the same as that angle. And again, if you're unsure about dot product, then you can go and check it out in the snippet section. So we can now replace the cos theta with the n dot k. So then we're able to write that AB is going to equal AB dash upon n dot k. So that means that we can rewrite our area, delta SL is going to be equal delta RL upon the n dot k. So let's rewrite this out in full. If we had some scalar function g of x, y, z, and it's a scalar function that we're finding the surface integral over some surface, then we can write that then as the sum from the L elements from 1 to n of the scalar function times delta RL upon n dot k. And then if we take the limit as the n tends to infinity, that is the number of these little surfaces tends to infinity, and the area of the surface tends towards 0, sorry, that's looking at this surface here, tends towards 0, then this is going to give us the double integral over the region R of our function, our scalar function, divided by n dot k times dx by dy. But we're looking to find just a double integral, but we've got a function here of x, y and z. Now we don't want a function of x, y and z, we only want a functions of x and y, because we're going to be different. We're going to be integrating with respect to x and y. But we know that z is just a function of x and y, so you can actually write z as a function of x and y. And you can do the same down here for the normal component, where z is still going to be a function of x and y. So now we've got to this point here, but we know that this n dot k, well, we know that the normal vector n from the last video, we derived the normal vector, and it can be written as minus I partial f by partial x minus j partial f by partial y plus k upon the root of 1 plus partial f by partial x squared plus partial f by partial y squared. So we're taking this here, which is a normal component, and we're taking the dot product with the component vector k. Then we can see that the I dot k is going to be 0, and the j dot k is going to be 0, and the k dot k will give us a value of 1. So it's just this, we're left with this here. So now we can put this here in for n dot k. But of course n dot k is in the bottom line, so it means that the 1 over, this will head up onto the top line. So finally we're going to be left with this equation here. So we've got our original surface integral of our scalar function. Now that's equal to the double integral over some region of our same function, x, y, f of x, y, times this value here, the root of 1 plus partial f by partial x squared plus partial f by partial y squared plus 1 dx dy. So this part here is a surface integral over some surface S, and that is equivalent to a double integral over some region r. Now here's a little example. Let's say we're looking for the surface integral of some function z squared, and we say the surface we're looking at for it is x squared plus y squared plus z squared equals 1. Now that surface is going to be the surface of a sphere. Now let's take the projection of that sphere down on the xy plane. So we're looking down here, and it's a quarter of a sphere, and we're taking it, looking it down onto the xy plane here. And we can then write z as a function of x and y, so we're just rearranging this such that it equals the positive root of 1 minus x squared minus y squared. So now what we can do is we can take the partial f by partial x, and I've derived that there, it's minus x upon z, and the partial f by partial y by a similar method is minus y upon z. So we can put these in for these values up here, and we end up with our root of 1 plus x squared upon z squared plus y squared upon z squared. Okay, so that then is going to equal our value 1 upon z. So let's continue this on the next page. So we can then write the surface integral z squared is the same as the double integral over the region of z squared times 1 upon z dx dy, which is equal to the double integral of r over region r of the root of 1 minus x squared minus y squared dx dy. So this here is an easier integral to deal with, so we can work through this integral in order to get a value for the surface integral here. Now we're almost there. We've worked out how we can evaluate the surface integral. So what we can do is we can just replace our function g of x, y, z with our scalar function f, and with the dot product n, so it's f dot n. Now we want to look at this surface integral in terms of a double integral over some region. So we'll just rewrite it out as previously. We're going to have some function, this vector function f, and it's the dot product of vector function x, f, in the normal direction, and we're taking the surface integral of that. So that's going to be equal to the double integral over some region of f dot n times the root of 1 plus partial f by partial x squared partial f by partial y squared dx dy. So we've seen that just in the previous page. But now we note that again the normal component can be written in this form as derived in the previous video. So now what we can do is we can take this here and we can replace the n with this here. But then what happens is all of this here cancels with all of this here. And then what we're going to be left with is the double integral over some region. And if we take these components here, so there's going to be the component of our function in the x direction, so it's minus the component of the function in the x direction times partial f by partial x, and it's going to be minus the component of the function f in the y direction, partial f by partial y, plus the component of our function f in the z direction times dx dy. Now let's look at an example of using this in order to find the surface integral. Let's say we're looking for the surface integral of some function f dot n ds, where the function, the vector function, is given by I of z minus j of y plus k of z, and the surface we're looking to project onto is going to be s equals x plus 2y plus 2z equals 2. So we can then write this function out here, z as a function of x and y, just by swapping the variables around. So we have 1 minus x upon 2 minus y. So then what we can do is we can take the partial f by partial x, which just gives a half, partial f by partial y, which gives us minus 1. So this integral here, the surface integral, is equivalent to the double integral over a region, and we're just going to have our values here. So we're going to have our value of our minus a half for partial f by partial x up here, and the minus f of x, well, minus f of x in this instance, the minus f in the x direction is just going to be the value z. Well, z is, will be seen as 1 minus x upon 2 minus y, and the same thing for this component here. We've got a partial f by partial y, which is just value minus 1, times our minus f of y. Okay, so the minus cancels with the minus here, makes a plus, and that's just our value of y, so that's the y component. Plus the last section here is just f of z, which f of z from our vector function is just our value x, times dx dy. Now whenever we multiply all this out, you end up with a double integral over some region of 3x upon 4 minus 3y upon 4 plus a half dx dy equals a half. And the dx dy, and whenever you work out that value there, and that value is over some region, and the region it's over, the projecting onto the xy plane, the yx plane, is just gives us this little value here. Okay, so this here is just the projection onto this little area element in here. Okay, so you're projecting that surface down onto that area element. Okay, so that value then in the end, when you work that integral out, is equal to a half. Okay, so that's the last section on the surface integral. It was a longer video. Next video will be a bit shorter, and we're going to go and look at the idea of the flux. Okay, thank you for listening, and if you enjoyed the video, don't forget to subscribe. Goodbye.